definition, right? So the definition of a linear transformation. So a transformation is linear if it satisfies these two conditions. Now let's see how many of you can remember the properties which we have discussed in the previous session and try to answer this question. Which of the following is a linear transformation? Take a couple of minutes and try to answer this question. So how many of you remember the general form of a linear transformation from R2 to R2? There are some answers except A and D which has XY term. Yeah, very good. So just let's see the how many of you can recall the general format of T of X comma Y. Can anyone tell me what is the general format? So any linear transformation from R2 to R2 should be of this form: AX plus BY, CX plus DY, right? So this is the general form of a linear transformation. Now here in the first option, you have the product of X and Y, which is not allowed, right? So this is not possible. This is fine, but this is not possible. So this cannot be a linear transformation. And this one is completely fine. It is of this form only. So this is fine. So C is also fine because here you see that actually the value of A, can you say what is the value of A in this case? When you compare it with this particular expression,
By 2.
what is the value of B
Is 0.
and what is the value of C?
Again 1 by 2.
No, C is 0. Coefficient of
Zero,
X
zero.
is 0. Yeah, and D is 1 by 2, right? Okay, good. And again here we have the xy term which is not allowed. So this is not a linear transformation, right? So this is clear for everyone, right? Yeah. So why these two are linear transformation and why these two are not linear transformations? I hope this is clear. So let me maybe add another simple example here and tell me whether it is a linear transformation or not. Is this a linear transformation?
Yes, ma'am.
Okay, so this is a linear transformation because here this is a real number, right? So any real number is possible, right? So this is fine. Okay, so let me maybe give another example. What about this? Is this a linear transformation? No, right?
No.
Yeah, good. So this is not a linear transformation because so powers of x are not allowed, right? So this is not correct. All right. So we understand what is a linear transformation. So next is mode is different, I guess. Okay. So what is the matrix of a linear transformation with respect to the canonical basis? You know that you have to find what is TE1 and TE2. So you write what is TE1, that is the first column, and TE2 is your second column, right? The coordinates of TE1 and TE2. Remember, this is the matrix with respect to the canonical basis. Remember that. This is not any matrix representation. This is with respect to the canonical basis because at the end of this session, we will be seeing what is the matrix representation of T with respect to any other basis, in general, any basis. Okay, so we will see that. So this particular thing is with respect to the canonical basis. What is canonical basis? These two vectors are called the canonical basis, right? Okay. So, and how to get back to a transformation from a matrix? So this is how we get back to a transformation. Okay, so where this a matrix, given matrix, we are considering it as a matrix with respect to again canonical basis, right? Okay, fine. So now go through this question and see whether you are able to understand the statement first of all given here, and then try to answer. First, let's see how many of you are able to understand the question. If you are not able to understand the question, please raise your hands. I'll try to explain and then you figure out the answer. It's very simple only. Some errors here. This should be. Okay, so most of
C.
you have the answer as C. Good. Okay, so because what is happening? So any vector V is simply mapped to 10 times of V. So TE1 is 10 times of TE1. So it is simply 10 comma 0. Similarly, TE2 is 10 times of E2. So 0 comma 10. So 10 0, 10 0 0 10. So this is the correct answer. Right. So remember this is TE1 and this is TE2. Okay. Fine. Similarly, let's try this one. So suppose let us say this is U1, U2. What is the relation you see between this and this? Similarly, this and this. So, and if this is V1 and V2, what is the relation you see between the first coordinate and second coordinate in the second case also? So, see that and you will be able to figure out. Yeah. So, V. It's not exactly a scalar multiple. Scalar multiple means entire vector is multiplied by one number. But here some scaling is happening, but it's not exactly scalar multiple. Okay. So here you can notice that U1 is mapped to 3 times of U1. Similarly, U2 is mapped to 2 times of U2. Same way, V1 is mapped to 3 times of, this is 3 times of V1. And this is 2 times of V2. Right? And you see that this in general forms a basis. Actually, there is a much like formal way of doing it, but yeah, from this itself we can have an idea. So you can see that T of 1 comma 0. So the first coordinate should map to 3 times of the coordinate. So it should be 3 comma, and the second is 2 times of that. So it's 0 component, so it's 0. And similarly, T of 0 1, you see that when we multiply anything with 0, it's just 0, and the second component should be multiplied with 2. So it's 3 0 and 0 2, right? So 3 0 0 2, this is the answer here. Okay, so is this fine for everyone? Yeah. All right, shall we move to the next one? Is this fine? Shall we move on? Okay. Yeah.
Yes, ma'am.
So look at this question now. Okay, Shonali has asked me to explain again, right? So Shonali, you are asking about this question, right?
No, ma'am,
So here,
understood, ma'am.
okay, okay, fine, yeah. This is again a simple question. Are you all trying?
Yes.
Note that the first column is representing the coordinates of T1 and second is representing T2. Remember that you have a 1 by root 2 multiplied to all these numbers. Keep that in mind. So can anyone first of all tell me what is TE1? Yeah. So TE1 0 root 2. Okay, so you're giving the final answer. Okay, let's check that. So TE1 is first of all 1 by root 2 comma 1 by root 2 and TE2 is minus 1 by root 2 comma 1 by root 2, right? And how can we write the given vector 1 comma 1 in terms of E1 and E2? 1 comma 1 in terms of E1 and E2. How can you express this as a linear combination of E1 and E2? What should be the coefficients here for E1 and E2? They are simply 1 times of E1 and 1 times of E2.
One,
Very
madam, one.
straightforward. Yeah, so E1 plus E2. It's basically E1 plus E2, right? So T of 1 comma 1 is simply TE1 plus TE2. So it should be 0 comma 1 by root 2 plus 1 by root 2. What will you get? First coordinate, it gets
Root
cancelled.
2.
So second, 2 by root 2. So it is root 2. Okay, fine. Is this fine for everyone? Okay, shall we move on? Okay. So the next topic here is what is the range of a linear transformation? So you all know what is the range of a function, right? So maybe we'll take a simple example and see how many of you remember what is range of a function. Suppose let us say f of x, f from R to R. Okay, simple function f of x equal to f from R to R and f of x equal to x square. Can anyone say what is the range of f?
All possible linear combinations.
Come on. This is just a function. There is no concept of linear combinations for just a function. I'm just talking about a simple function. I'm not talking about any linear transformations. Just the basic concept of a function and the range of a function. So by
0
definition,
centimeter.
yeah.
Ma'am,
0 cent.
1 to
Infinite.
1 to infinite. Okay, please mute. So it is actually by definition, it is a set of all f of x such that x is in R. Okay, so you take any real number. What is the minimum value of this x square? Is there any minimum value first of all for this x square?
Positive value, madam.
Yes.
0.
Yeah. So it means the minimum possible value is 0. What about the maximum possible value?
Infinite.
So this is the range, right? So it is set of all f of x such that x is in the domain R, right? And you find out what are they. So the exact same definition applies for a linear transformation as well. So range of t is set of all tu such that u is in R2. So here this represents the domain of the function. This R2 here represents the domain of t. Okay, fine. So range of t is set of all tu such that u is in R2. Okay. So if you have a linear transformation, then t and te1 is a comma b and te2 is c comma d, and you have this matrix representation. Then what is range of t in terms of these vectors? So it is nothing but the spanning set of spanning set te1 te2. Okay, so it means what? So now first of all, range of t, whether this will have a spanning set or not. When can we say that a set will have a spanning space? We can talk about spanning sets only for subspaces, right? So first of all, range of T is a subspace and this subspace has a spanning set. So can anyone recall what is the condition for a subspace?
Any linear combination equals to the subspace.
Should be inside the subspace. Yeah. So any linear combination you take, it should be inside the subspace. So here, why this range is first of all a subspace? Range is a subspace because let's take any two elements here. So let's say T of U and let's say T of V. These two are elements in range of T. Now, what about alpha T of U plus beta T of V? Now, using the properties of T, we can rewrite it as T of alpha U plus beta V. And U and V are there in R2. So U comma V belong to R2 implies alpha U plus beta V belongs to R2. Right? So in that case, if alpha u comma beta plus beta v belongs to R2, then you know that T of alpha u plus beta v belongs to range of T. Okay, so this says that this is a subspace of R2. So from this we can say that this is a subspace of R2. Range of T is a subspace of R2. Okay, now since this is a subspace, we can find a basis, a spanning set we can find. Okay, so what is the very simplest spanning set we can think of? It is simply te1 and te2. Okay, because e1 and e2, you know that it forms a basis of R2. Te1 and te2, we cannot say it forms a basis, but it will form a spanning set for the range. How can we say this? What is meant by spanning set? Can you recall what is a spanning set? What is a spanning set? So spanning set definition. So let's say if you say that S is a spanning set if, let's say, of a subspace V. This means what? You take any vector from V, then let's say the elements of S are some V1 and V2, for example. You can write V as alpha V1 plus beta V2. This is the meaning of spanning set. Now we are saying that range of T, this TE1 and TE2 is a spanning set for range of T. right? This means what are we claiming? We are claiming that if you take any t of u, you can express it as alpha te1 plus beta te2. This is what we are claiming. Okay, because we are saying that this is a spanning set, so we are claiming this. So here this is the explanation. So let's take any t of u. First of all, u we can write it as xe1 plus ye2, right? So let's say your u is some vector x comma y. Then you can write u is xe1 plus ye2, and tu is simply x te1 plus y te2. So you have already found what are your alphas and betas, right? Very straightforward. Yeah, so you see that this is a spanning set. Okay, all vectors in range of t are linear combinations of te1 and te2. Okay, so range space for the matrix M of t, range or range space or column space is the span of the columns. Remember, all these terms are same. What is the range of t, what is the range space, what is the column space, everything refers to the same. Everything refers to the span of the columns. Okay, everything refers to the span of the columns. Okay, span means all possible linear combination. Okay, fine. Now we will see some examples here. So before looking at the examples, we will have one more definition here. What is rank of a linear transformation? Okay, so rank is simply what is the dimension of this range. Dimension of this range is the rank. Okay, because we saw that this is a subspace, right? So range of t is a subspace, so it means it will have a dimension. So the dimension of the range of t is the rank of t. Okay, fine. And we can say the dimension of range of t is the rank of the matrix as well. Okay, so for basis for range of t, you have to do the elimination process to find the you have seen the elimination process in week 1. So if you want to find a basis for range, then you have to do the elimination process. So here we have some examples. We will try to understand what is range in a more better way. So before that, can you say what is the least and what are the possible values for rank of t, where t is from r2 to r2? What are the possible values? So you have t from r2 to r2. What are the possible values of rank of t? Remember that your range of t is a subspace of R2. So the dimension of range of t is rank. So what are the possible values for rank? Can you say it now? You already know what are the possible values of the dimension of any subspace of R2. So what are the possible values? Come on. Yeah, good. Sonali has answered. Good. So the possible values are 0, 1 and 2. So these are the possible dimensions of any subspace of R2, right? So if it is the origin alone, then 0. If it is a line passing through origin, the dimension is 1. And if it is the whole space, it is 2. So these are the only possible subspaces of R2, right? Okay. Now we are going to find a basis for the range of a linear transformation represented by the following following matrices. Okay, fine. So now for this matrix, you see all the entries are 0. Okay, so if all the entries are 0, so let's maybe give some names. So let's say this is A, B, C, D. These are A, B, C, D matrices. I'm giving names. So now with these names, let's say you have A of what is E1. Maybe instead of ABC, let me say T1, T2 because I'm going to talk in terms of T, right? So let's write it as T1, T2 and so on. So T1, T2, T3, T4. Yeah, now tell me. Now what is T1 of E1? What is T1 of E1?
0 0.
And what is T1 of E2?
Obviously 0 0.
Okay. So what is the range of T1?
0.
It's just the zero vector, right? So in this case, what is the rank of T? What is the rank? For the just the origin, the rank is
0.
0, right? And what is the basis for this? Is there any basis?
No, ma'am.
Remember, if it is just the origin, there is no basis. Okay, because zero vector alone cannot form a basis because it is not linearly independent. Okay, fine. Now, what is T2 of E1? This is T2. So, what is T2 of E1?
1 0.
Yeah. And T2 of E2?
0 1.
All right. So, what is range of T2? It is the span of 1001. So, what is the span of 10 and 01?
Whole R2.
R2.
So, what is the rank of T in this
Rank will
case?
be 1.
Rank is?
Sorry. 2.
All right. And in this case, what is the basis?
1 point.
Just these two vectors, right? E1 and E2.
In
1, 0.
different direction.
These two, any two vectors you can take. So, this is one basis. Yeah, any two linearly independent vectors you can take. So, here we have a straightforward scenario. So, we can directly take this also. Okay. What about T3 of E1? What is T3 of E1?
1 3.
And what is T3 of E2? 2 comma 4, right? Now, what is range of T3? It is the span of,
R2.
yeah, 1, 3 and 2, 4. What do you know about 1, 3 and 2, 4? Are they linearly independent?
Yes, ma'am. They are linearly independent.
So, if they are linearly independent, what should be the span?
Entire R2.
Yes. And again, the rank is 2, right? Okay. And what about the basis?
Any two linearly
Basis.
independent vector.
Yes. In fact, you can simply take these two vectors here.
Or we can write any vector which is linearly independent.
Yes, yes. Any two linearly independent vectors is fine. Okay.
Okay.
What about T4 of E1? So can you,
1 3.
and what
1
is
3 and 2 6.
yes. So now
Range
in
is
the
a span of 1.
yeah
Is the
range of,
line.
yeah. So it is span of 1
Span
comma
of
3 and 2 comma 6. But you note that 2 comma
This is a
6 is,
line.
yeah. So 2 comma 6 is simply 2 times of 1 comma
Scalar
3.
multiple.
Yeah. So it means it is a straight line. Yeah. So straight line, line through origin. This is a line through origin, right? So here, what is the rank? Rank is
1.
1. And what can be a basis in this case?
Only 1 point on the line which is not 0.
Yes. So any point on the line. So we can pick maybe 1 comma 3 here. Okay, or 2 comma 6 also works. So I'm taking just 1 comma 3. Okay. Fine. All right. So What is the so up to this, I hope it is clear now how to find the range, basis of the range, and rank. I hope it is clear now. Now we'll see what is full rank matrix. A 2 by 2 matrix is said to be a full rank matrix if the rank is 2. Okay, so here we can see that these two are full rank matrices, right? So you see this is a full rank matrix and this is also full rank matrix because here the ranks are 2, right? So rank of T is 2 if and only if TE1 and TE2 are linearly independent. Okay, so when we apply the elimination process to this TE1 and TE2, you will get two non-zero columns in that case. Okay, fine. So is the concept of determinant already introduced or not? Yes, Shonali.
Could you please explain the rank in question number 2 and 3?
This one, why they are full
Yes,
rank?
ma'am.
So here the rank is 2. Is that clear?
Yes, ma'am.
So now if you take any 2 by 2 matrix and if the rank of that 2 by 2
No,
matrix is
ma'am.
2,
That how the rank is 2 in both
how
the
the rank?
questions.
Okay, see, rank is the dimension of range. Okay, so dimension is the number of linearly independent vectors in any spanning set. So now this is a spanning set, and in this spanning set, how many linearly independent vectors are there?
2.
That's why rank is 2. Same here also. In the spanning set, we have two linearly independent vectors. That's why the rank is 2. So the number of elements in basically the basis is the rank. Okay, fine.
Yes,
This
ma'am.
is not just about rank. In general, for dimension, this is the concept, right? Dimension, the definition is the number of elements in the basis of the subspace. All right? Okay.
Yes, ma'am.
Okay. So is the concept of determinant already introduced or not?
No, ma'am, not yet.
Not yet. Okay. But this is good to know at this point, I feel. So it's a very simple thing. So maybe you all know it already, I guess. How many of you know what is the determinant of a 2 by 2 matrix? Forget about the higher order. 2 by 2, how many of you know? Can you raise your hands? Okay, what about the others? 2 by 2 matrix determinant? Okay, no problem. It's a very simple thing. Okay, few hands I see. Okay, fine. So, if you take a matrix determinant, okay, of a 2 by 2 matrix ABCD. So, determinant of A is AD minus BC. Okay, it's what? AD minus BC. Remember, determinant is simply AD minus BC. Okay, so for example, if I'm giving 1 minus 1, 2, and 3, what is determinant of A?
5.
So it is 3 minus 2, so it is 5. Okay,
Excuse me, ma'am. Sorry, I'm
yes,
interrupting you, but I have a doubt in the you have solved in above question.
yeah.
The linear above. Scroll it up little bit up, ma'am. Linear transformation. This one. This one. I 1 comma 1 is equals to 1 e1 plus 1 e2.
Mm.
This I understand, but the last one t1 comma 1 is equals to te1 plus te2. I didn't get it.
Okay, see, this is suppose you are having u is equal to alpha x plus beta y. So maybe alpha e1 I will take them. So alpha e1 plus beta e2. Okay, then t of u is alpha t1 plus beta t2 from the properties of linear transformation. This you understand, right?
Yes, ma'am.
So here there is a 1 here, that's all. Multiplying a 1 is not making any significant change. So I have not written the 1 here. That's all. Is that
But the
fine?
answer is 0 comma root 2, where this
Yeah.
is.
What is TE1? What is TE1 here? Your TE1 is 1
Oh,
by.
okay, okay. I got it. Now I got it. I have
Okay.
not putting the value of T1 and T2.
Okay. Okay. Fine. Fine.
Oh, thank
Okay.
you.
Substituting it, you will get. Okay. Good. Good. So where were we? Yeah, determinants. Now, can you just tell me what are the determinants of these matrix given here? What is determinant of T this matrix? Let's say A. What is
Zero.
determinant?
Zero.
Let's say determinant of A1 is 0. Okay. What is determinant of, let's say, A2? What is
One.
determinant of A2?
One.
A2 1. What is determinant of
Minus
A3?
2.
Minus 2. 4 minus 6 minus 2. Okay.
Zero. Last
And
one is
A4, the
zero.
determinant of A4 is 0. Okay. So what is that you notice? So in this case, the determinant is non-zero. In this case also, the determinant is non-zero. So you see that a matrix is full rank if and only if the determinant of the matrix is non-zero. Okay. Full rank is possible only if the determinant is non-zero. Okay. Fine. So just something you can remember. There is much more we can see about determinants in later weeks. Just since this is something very much important in understanding the rank, I have introduced it quickly here. Okay, we are going to see the determinant topic in detail in later weeks. Okay, fine. All right. What is null of a linear transformation? Okay, so null is saying what are the set of all values in the domain, okay, values in the domain which are mapped to just the origin. Okay, what are all the values, what are the vectors in the domain which are mapped to origin. Okay, so the basic difference between range and null is that the basic difference, range is a subset of codomain. Okay, but null is a subset of which one? Null is a subset of the domain. Okay, the set of all vectors in the domain such that tu is equal to 0. Since here both the domain and codomain are same, in this particular scenario you might not find any significant differences. But later on, when you have transformations from different domain to codomain, you will understand the significance of this point which I am telling now. Okay, so null is a subset of the domain. Okay, and null is also a subspace. How null is also a subspace? Because you see any two vectors you take and take their linear combination, then what happens to t of this linear combination? You can write a tu1 plus b tu2, and since u1 and u2 belong to the null, you know that tu1 is 0 and tu2 is 0, and hence a tu1 plus b tu2 is a times of 0 plus b times of 0, 0. Okay, so that's why you see that. So because of this, you can see that au1 plus bu2 belongs to null of t, and hence null of t is a subspace. Okay, and what is nullity? Nullity is the dimension of null of t. Okay, so nullity is the dimension of null of t. Just like rank is the dimension of range, nullity is the dimension of null of t. So null or null space we say. All right. Okay. So how do you find the null space of a matrix? Okay, so this is something very much related to system of linear equations. So let's say this is the matrix representation of T with respect to the canonical basis. Now what is the null space? Null space is a set of all vectors x comma y such that the matrix times of x comma y equal to 0. So when you are writing this matrix as A, so this is basically set of all V. So let's say V is, this is your V. Suppose this is your V. Okay, and this is A, let's say. So what is your set becoming? Your set is becoming set of all V such that AV equal to 0. Okay, so this is simply, so null of A is basically the solutions of the homogeneous equation Ax equal to 0 or Av equal to 0, anything is fine. Yeah, so someone raise your hands, please ask your question.
Ma'am, the question is, you are telling the dimension of range is rank, right?
Yeah,
Can we say it also the dimension of vector, whether it is in 1D, 0D, or 3D?
dimension of what?
Vectors, or it is in dimension, right? So 1D, 2D, and 3D we can say, or
0.
is it a defining term? The dimension of a range is rank.
See, what you are saying is 1D, 2D, 3D, that's what I'm saying is dimension. So it's basically the same. So I'm saying here the dimension is, rank is 2, so this is a two-dimensional space. And here the rank is 1, so this is a one-dimensional space. Line is a one-dimensional space. R2 is a two-dimensional space. Did I answer your question? We have not yet gone to 3D. What are 3D? We have to look at R3 for 3D, that we have not yet seen. Did I answer your question?
Okay, okay, got it.
Okay. Okay. So what is null space of a matrix? Null space is set of all V such that AV equal to 0, or you can say solution of the homogeneous equation. Maybe let's better put AV to avoid confusion, because here X is just one coordinate, right? So AV equal to 0. Okay, fine. So how do you find the null space? You have to solve the system of linear equations. So you just see ax plus cy equal to 0, bx plus dy equal to 0. You get a system of linear equation. You solve this, you find the null space. Okay, we have some examples to do this. So to understand this, so here, these are some examples which we have seen earlier. So only one more example is here. So for this, why the rank is 1? Can you all see why the rank is 1? Why the rank is 1? Is that clear?
Yes, ma'am.
Yeah, because here you see that this is TE1 and this is TE2. So this is a zero vector. It does not contribute anything in the spanning set. So only this vector is contributing, and you have this as a basis for the range. So only one vector in the basis of the range. So the rank is 1. So in this case, the basis of range of T is simply 1 comma minus 1. So you have rank is 1. All right. Okay. So now how are we going to find the null spaces? Okay. So first let's try to find the null spaces. So of the matrices we'll find. So A1, A2, A3, A4, A5. So what is null of A1? So null, null of A1, how do you find? Is the set of all V such that AV equal to 0. Okay, for which V AV is 0 for this matrix A1V. For what are all V's, A1V will become 0. It's a very trivial question I'm asking here. So this is a 0 matrix. Okay, now no, think more clearly. Say I'm having a 0 matrix. What are all the vectors be when I multiply with this matrix will result in 0? 0 is one possible answer. But what are all the vectors satisfying this condition? Suppose I am taking any vector x comma y. I am multiplying with 0, 0. What will I get?
0.
0, right? So it means any vector v is possible, right? Yes or no? So what should be
The
this?
answer is all the possible vectors put it into
So it's entire
or
R,
R2. R2.
right? It's the entire R2. Okay. So if this is the entire R2, then what is the nullity? What is the nullity?
2.
Nullity is 2. Okay. Fine. Now, what is null of A2? It is a set of all V such that A2 V equal to 0. Right? So now you have 1 0 0 1 times xy equal 0 0, which means you have x is equal to 0 and y is equal to 0. So it means the only possible solution in this case is 0 0. This is the only possible solution. Okay. So here what is the nullity? Nullity
0.
is 0. Okay. Fine. What about null of A3? Again, it is set of all V such that A3V equal to 0. Right? So here what is A3? A3 is 1, 2, 3, 4, right? 1, 2, 3, 4 into xy equal to 0, 0. So here you see x plus 2y equals 0 and 3x plus 4y equals 0. Now, how do you usually solve this kind of equation? Let's multiply. Let's call this as equation 1 and this as equation 2. Multiply first equation with, let's say, 2. Then what will you get? 2x plus 4y equals 0. And second one is 3x plus 4y equals 0. Now I'm going to subtract. If I'm subtracting, this part will become 0. I will get minus x is equal to 0. So this means x is equal to 0. Now if x is equal to 0, then x plus 2y equal to 0 will imply 2y equal to 0. So y is equal to 0. So again, what is the only possible solution in this case?
The null vector and the nullity is 0.
Yes. So in this case, again, nullity is 0. Okay. What about null of A4? Okay. So before looking at the null of A4, let's try to see. Maybe we'll complete this and then for A5, let's do the guess. A4 V equals 0. Okay. So what is A4? It's 1, 2, 3, 6. So you have x plus 2y equals 0 and 3x plus 6y equals 0. So you see that if this is equation 2 and this is 1 and this is equation 2, you can clearly see that equation 2 is simply 3 times of equation 1. So represent both 1 and 2 are same line. They are representing the same line, right? So in that case, you are looking at all the points on the line. Which line? X plus 2y equal to 0. So here, all the points on the line x plus 2y equals 0. Or if you want to rewrite it, maybe you can rewrite it as set of all x comma y such that y is equal to minus x by 2. So again rewriting x is in R. Why I am doing this rewriting, you will understand. How do I find a basis for a given line? So this is one way, and you will see that this method will work even if you are working in R3, R4, R5, right? In higher dimension also this technique is going to help you. That's why I am following this technique from here. Maybe this is a case where you don't need this technique, but still, if we follow this, this is going to help us in the future also. So how are we going to find a basis in this case? So here the basis is entire R2, so any two linearly independent vectors. Here for these two there is no basis, but for this, what is the nullity in this case? It is a line
One.
passing through origin, so nullity should be 1, right? So the nullity is 1.
1.
So it means the basis, you have one vector. How do you find a basis vector? So here the simple technique is that you take this x commonly, and then you have 1 comma minus 1 by 2. X is in R, and this gives one basis. So 1 comma minus 1 by 2 is a basis. So this is a technique to find basis. Okay, fine. So now what is the observation we are having here? Here for this case the nullity is 2, this case the nullity is 0, this case the nullity is 0, this case the nullity is 1. So what do you observe? In each case, what do you observe? When you add the rank and nullity, what do you observe? In every
We are
situation,
getting 0. 2.
2. So can you guess what should be the nullity in this case?
1.
Yeah. Okay. So if you know what is the rank or nullity, can you guess what is the other one? Yeah.
Yeah.
Because we have the rank nullity theorem, which says rank plus nullity is equal to 2. So if the range is entire R2, then the null space is origin. If the range is aligned, then the null space is also aligned. And if the range is origin, the null space is entire R2. So in this case, you can see in both these cases, the range is just aligned. So here it is span of 1, 3, here it is span of 1 minus 1. So similarly, the null space is also span of one single vector. So hence, you see both rank and nullity are 1 in this case. Both are lines through origin. Okay. So these are the only possible scenarios for range and null for a transformation from R2 to R2. Is that fine? Yeah. So up to this, the range and null space concept, is this clear for everyone? So far we have seen what is mean by range, what is mean by null, and these two are subspaces. Okay, these two are subspaces. The dimension of range is rank, the dimension of null space is nullity. Okay, and rank plus nullity is equal to 2. Okay, fine. Okay, let's see some problems. So read this question, take a couple of minutes and try to answer. It's a very direct question.
Hello, hello. I'm not able to.
Yeah. So what are the solutions here? One, option A, you see that obviously it's correct, right? Because
Option A and option D, I think. Right.
option C also, right? Only this is incorrect. You know that any sum or scalar multiple will also be in the null space. So it's actually a subspace. It's given it's not a subspace, so it's incorrect. Similarly, if you take the sum of any two vectors in the range, then that's also in the range. And that forms a subspace. Right? Yeah. What about this question? So for this, can you tell what is TE1? What is TE1?
X0.
No, so TE1 is T of 1, 0, right? What is T of 1, 0? It's simply 1, 0, right? Yeah. And what about T of E2? T of E2 is 0, 0, right? T of E2 is 0, 0. Now from this, can you say what is the range of T? Range of T is span of? What do you mean by 2? I'm asking what is the spanning set for range? You are having a zero vector and a non-zero vector. When you take the spanning set, in spanning set we don't take the zero vector, right? It does not contribute anything actually if you take the zero vector. So what is the spanning set for range of T here? Which of this following option will match?
T.
Yeah. So you see that this is matching, but this is not matching, right? So we can see what is the range. And now for looking at the null space, so we have to see when is your T of x comma y 0, 0, right? So it means what is T of x comma y? T of x comma y is x comma 0, which is 0, 0. So this implies x is equal to 0. So this means your null of T. So if x comma y belongs to null of T, then you have this, and so you have null of T is equal to set of all 0 comma y in R, right? And this is the span of 0 comma 1, right? So you see that this is correct, and this is already we have rejected this because it's incorrect, and this is incorrect. So this is the correct option. Is this fine for everyone? Yeah. Not option A, option C. Is this fine?
Can you please explain once again
Yes.
the second part, null of T?
Yeah. So what are the elements in the null? We can either follow this technique or you can use the matrix method also. Maybe I'll tell the matrix method also. So first let me explain this part which I have already explained. So what are all the vectors which are there in the null we want to see? So I am randomly taking some arbitrary vector from null. Then we know that according to this definition, null space of T is set of all x comma y such that T of x comma y is 0. Now, what is T of x comma y? T of x comma y is given as x comma 0. So, in place of T of x comma y, I am putting x comma 0 and equating it with 0, 0. and I see that x is equal to 0. So what is null of t? All the vectors x comma y where x is 0. So I'm replacing x with 0 here. And you know that this is simply the span of 0 comma 1. Okay, I will write it more clearly here. 0 comma 1. Yeah, because you can
So
write.
the first line x comma y is equals to null of t is the definition you are telling, right?
Yeah, so because here you see that null of t, the definition is set of all x comma y such that t of x comma y is equal to 0. Okay, so what are all the x comma y which are there in this set I want to see. So I'm taking an arbitrary vector to see what is happening. So just like we did in here, we are taking some arbitrary vector x comma y, we substitute and find it, right? So that arbitrary vector instead of the matrix, now I'm dealing with the transformation, that's all. Okay,
Got it, ma'am.
yeah. So now the same thing can be done with matrix also. Now what we already know what is te1 and what is te2. So what should be the matrix for t then? We already know te1 and te2. Can you tell what is the matrix for this transformation?
1000.
Yeah, so this is the matrix.
1000.
Yeah. So now from here also you can get the same answer. So you multiply x comma y, equate it to 0, 0. Then you will see that you have x is equal to 0. So you again get the same. So this implies, so from here again you will get the same. Fine. Okay. So either you can use this technique or this technique, whatever you find it convenient, you follow that. Okay. So most people prefer the matrix technique. I also recommend using matrix. That's convenient also. Okay. Fine. Okay. I guess this is fine and we can move on, right? Okay. Consider a matrix 3 minus 1, 2, 5 which represents a linear transformation T. Find the rank of T. How do you find the rank of T?
Ma'am, since the TE1 and TE2 is linearly independent, so we can say that this is a the rank will be in R2.
Rank is 2. Range is R2 and rank is a number.
Okay.
Yeah.
Rank is 2.
Yeah, good. So rank is 2. Yeah. What he said is correct because TE1, this is TE1 and this is TE2, and TE1 and TE2 are linearly independent and hence rank is 2. What is the other technique which I told you?
The
Can anyone?
determinant is not 0.
Yes. What is the determinant in this case?
Mm, 17.
Yes. And it is non-zero. From that also we can say that the rank is 2. Okay. Fine. So how do you find, I'm just asking, so how do you find the null space of this matrix? Here the range is fine. Range is R2. What's the null space?
0.
Yeah, it's just the zero vector. Okay, fine. Okay, so moving on. I hope this question is clear for everyone. Any questions here? Okay, moving on to the next question. Everyone read this question. Take few minutes. Don't be in a hurry to answer. Take few minutes and answer. Definitely all ABC cannot be true, right? The rank and nullity should be unique numbers. They cannot take different values. See, this is the transformation given to you, the identity transformation. So what is
C, option C.
TE1? TE1 is option C. Okay. Why option C? Think about it. Okay. What is TE1? What is TE1? I'm asking what is T of 1 comma 0? What's the answer? Apply this
X.
transformation.
X, no.
No. Your
Comma,
X
1
is
comma 0 means.
it should be 1 comma 0 only. Whatever X come extend.
Oh, yeah, yeah. In that case, yeah, 1 comma 0.
And what is TE2?
0, 1.
0 comma 1.
0,1.
Okay. So you
I
see
was
TE1.
adding 1 into X like that, I was saying.
Okay. So now what is range of T?
Range is R2.
Yes. If range is R2, then what is the
Then
rank?
rank will be R2 and the nullity will be 0
Rank is
according to nullity and rank theorem.
okay. Rank is 2, not R2. Rank is 2. And then
Rank
again
is 2.
nullity
Is
should
0.
be 0. Okay. And here this is a very important transformation because what is the corresponding matrix here? Is the identity matrix. That's why the name of this transformation is the identity transformation. This is the identity matrix, right? 2 by 2 identity matrix.
It is
Right?
canonical, right?
See, 1001, that is the canonical basis. The matrix is called the identity matrix.
Yeah, yeah. Okay.
Okay, the vectors are the canonical basis and the matrix is identity matrix. So
I just got
option
this one.
A is correct. Okay, fine. Okay. So I hope this question is clear, right? Shall we move on? Yeah. Next question here. Find rank and nullity of T. So I recommend you to find what is TE1, TE2 and write what is M of T and then tell the answers. What is TE1? What is T of 1 comma 0 and 0
X
comma
minus 1. X minus y. X
again?
minus 1 comma 0 only, no?
Yeah, it should be 1 comma 0. And what is T of 0 comma 1?
0 comma 1.
No,
Uh,
don't be in a
mm,
hurry.
okay.
Your X is
0
0,
comma
Y
1.
is 1.
Minus 1 comma 1.
Minus 1, minus 1 comma 1.
Yes. Okay, so the
Excuse
matrix
me, ma'am.
is yes.
I'm stucking to solve this T1 and T2. Can you please clarify it how to deal with it? Because I do all the questions, but here I am stuck.
Okay, I understand what's your issue. So we are trying to find what is T of 1 0. Okay, so here we are putting X value is 1 and Y value is 0. So I am putting instead of X 1, Y is 0. Similarly, Y is 0. So I got 1 0. Same way, T of 0 1, now my X value is 0 and Y value is 1. So now x minus y, 0 minus 1 and 1. So I get minus 1 comma 1. Is
Okay,
that clear
got it.
now?
Okay,
Okay.
only putting the values in terms of
Yeah.
x and y.
Substituting a value.
Yes,
Okay,
yes.
okay.
Okay. Now,
Yep.
okay. So
What is
now,
this TE1? TE1 and TE2 are like my column vectors, or what?
yes, the column vectors of this matrix. Yeah.
Okay.
Okay. E1 and E2 forms the basis. So we are finding what, so always, as I told you in the very beginning, TE1 and TE2 forms a spanning set for the range. Okay, that's why we are finding what is T1 and T2 to find the rank. Okay, so now we have T1 and T2. Are they linearly independent? Are they linearly independent?
Yes, ma'am. They are linearly independent.
Okay, if they are linearly independent, what can you say about the range?
Entire R2.
Yeah, So it is the span of T1 and T2, and they are linearly independent, and hence it is entire
Uh,
R.
Ma'am, I want to hold you on here.
Yeah,
That linearly independent is there, right? Yeah, you're figuring out it by the determinant should not be equal to zero, right? If I'm not wrong.
that is one way, but that is not the only way. So you don't need the determinant to check the linear independence of two vectors. So let us say this vector is U and this vector is V. We are checking whether we can write V is a multiple of U or not. Can you write V as a multiple of U?
No,
No.
no.
Then they are linearly independent.
Okay, okay, understood. Because
Okay.
some cases, okay, ma'am.
Determinant is also one technique, but that is, yeah, next. This is the first basic definition. When you are checking linear independence of two vectors, this is what you do. Okay, fine. Okay, so now the range is R2. So rank is 2.
True.
2.
Okay.
Nullity is zero.
Yes,
Due
nullity
to
is,
true range theorem.
yeah. So rank plus nullity here, the answer is 2. Right? So 2 plus 0. Okay. This question is fine, right? Yeah.
Yes, ma'am.
Okay. So what we have seen so far, if we have a linear transformation T from R2 to R2, rank of T plus nullity of T is 2. So this is these are the only possible scenarios we can have. So if the range is a plane, then the null space is origin. If the range is a line, the null space is a line. And if range is origin, the null space is plane. So this is what we have seen so far. Right? And how to compute the range and null space, we have seen quite some examples now. By now, I guess the range and null of a transformation should be clear. So the next step, we are moving to range and null space of composition of linear transformation. So composition of linear transformation is simply like composition of just some functions only. Okay, so you know how to do composition of functions, right? So the composition of linear transformation acts in the same way. The advantage here is that the matrix representation is simply the matrix multiplication of the respective matrices. Okay, so suppose let's say you have two different transformations, and this is the matrix representation of S and this is the matrix representation of T. Then the matrix representation of S composition T is given by the product AB. Okay, and how are we defining the range and null? The usual way. So the range of S composition T is set of all S of T of V such that V is in R2. Now remember, what is the set of all TV such that V is in R2? What is this set? Can you remember? This is the definition of range of T, right?
So
Yes or
is
no?
it all the vectors written in R2? In R2.
All the
All the
images of,
linear combination of vectors.
not linear combination, all the images of T in R2.
Images of T.
Yeah, TV means image of T, right? Yeah, where V is mapped to from T. Yeah, so TV, set of all TV such that V is in R2, right? So now this TV I can replace with any vector here where that vector belongs to range of T because of this definition. Okay, so the same definition we can rewrite in a different way. So let's say this is W, then this W is in range of T. So instead of W, they have put the same V itself. Okay, just a matter of notation here. Now, what is null? Null in the usual definition is set of all V in R2 such that S of T of V equal to 0. Now, what is S of T of V equal to 0? Now, suppose you have here W, then SW equal to 0. What does that mean? What is the set of all W such that SV equal to 0? It is nothing but the null of S. This is nothing but null of S. Right? So here what they have done, they have said that all the set of all W such that the W is this T of V, which is in null of S. Okay, instead of writing S of T of V, These are just rewriting the set. Don't worry too much about this rewriting things and all. Okay, so just they have written the set in some other way. Don't worry too much about this part. Okay, fine. So this is about what is mean by composition of linear transformation. So if you have to, maybe one simple example, if you want, we can do. Did I do anywhere? Okay, so maybe I'll do it here. So very simple examples let us take. So let us take s of x comma y is x comma 0. Okay, and t of x comma y is x comma minus 6. Okay, so now what is s composition t of x comma y? It is s of t of x comma y, correct? So now what is t of x comma y? What is t of
X comma minus x.
x comma minus 6? Okay, now what is s of x comma minus 6? Remember, you have x is equal to x and y is equal to x is equal to x and y is equal to minus x. So here you have x and in place of y you have minus x. So what will you get here?
X comma minus x.
X comma
Minus x.
0.
0. Yeah, 0.
Okay, x comma 0 is what we will get here. The second coordinate should go to 0. That's all. Okay. Now s composition t of x comma y is x comma 0. So what should be the matrix representation of s composition t? What is s composition t of e1?
1 0.
1,
X.
right? What is s
uh,
composition t of e2?
0 0.
0 0.
0 0. Okay, sorry, 0 0. So the matrix here is m of s composition t is 1 0
1
0
0
0.
0 0.
Okay, now let us look at what is the matrix of S. Can you say 1 0?
0 0.
Same as mf s of t.
Okay, what is m of t?
1 0 0 minus 1.
1 0
0 minus
0
1. Minus 1.
minus 1. Okay, so here 1 0 you are taking. Why it is 0 minus 1 here?
Because your x is x comma minus x it is.
See here only the x value is coming. Y value when your x value is 0, what happens to both these terms? When you this is t of 0 comma 1, your y is 1, but here there is no y term. So what happens to the second?
0.
So the first vector itself is first of all 1 comma minus 1 and this is 0 0. Is that correct?
Okay. Okay.
Got it? See
For
what
the
is
t
1 0? It is
te2 is te1 is 1 comma minus 1. Why?
yes. Why? Because x is 1 and y is 0. And here I am having x is
Okay,
1.
so you are substituting. Okay, understood. Okay.
Okay, fine. This
Yeah,
is the
understood.
matrix. Now, what is the matrix multiplication of m of s into m of t? What is the matrix
1
multiplication?
0 0 0.
So you will get back this equation,
Yeah.
right? This matrix. So you can note that m of s composition t. So m of s composition t is same as m of s into m of t. This you can verify. Just the product of these two matrices. Okay. So what is the composition of linear transformation? I hope it is clear. Okay. Fine. So the next is what are invertible linear transformations? A linear transformation T is said to be invertible if there exists a linear transformation, another linear transformation T inverse here. Okay. which satisfies this condition that for every u, okay, where you have v equal to t of u, then t inverse of v is u. Okay, so if this you have, then you have t inverse of v is u. This is the definition of invertible linear transformation, and it satisfies this condition. When you compose t with t inverse, you will get identity. When you compose t with t inverse, you should get identity. Is that fine? Okay, so how do you find whether a matrix is whether a given transformation is invertible or not? So only when you have the matrix is full rank, it is invertible. Otherwise, it's not invertible. Okay. So only in this case, the first of all, T inverse will exist. When you have full rank, T inverse exists. Okay. In this case, T inverse does not exist. Okay, so when you have this case, okay, then you take any linearly independent vectors, t inverse of u1 equal to e1 and t inverse of u2 equal to e2. Then you see that if you have t of x comma y is xu1 plus y e2, then t inverse is this. Okay, so you can find inverse using the matrix. That is the most common way. So if you have, this is the matrix representation, and you have AD minus BC is not equal to 0. So here this is basically the determinant. The determinant is non-zero. Then the inverse of the matrix, you can find it in this way, right? Here, this is the determinant. So if I'm calling this as A, then this is the determinant of AD minus BC. Okay, and this is the inverse of the matrix. So how do you find the inverse of a transformation? Let's look at an example. See, suppose you have a transformation T of x comma y is equal to x plus y comma x minus y. Now what is m of t? Tell me, what is m of t?
1, 1, 1 minus 1.
Okay, now what is determinant of this matrix?
0. Minus 1, minus 2.
Minus 2.
And is non-zero. So it
0.
is full rank. If it is full rank, what do we know? Inverse exists, right? So T inverse exists. Now, how do you find T inverse? Okay, so to find the T inverse, you find the inverse of this matrix. What is the formula to find the inverse of this matrix? Use this and tell me. We already have computed the determinant. So 1 by minus 2. And what happens to this part? You should have, so this is your A, B, C, and D. So what happens? Your D should come here, A should come here. So minus 1, 1. And then B and C just changes the sign. So what is the matrix you will get? 1 by 2. I can bring the minus outside, so this minus gets cancelled. So 1, 1, 1, minus 1. Okay, so this is the inverse. Now, this is the inverse of the matrix. Now, from the inverse of the matrix, how will I get back the transformation? Again, very simple. You know that if you know the matrix, how will you get the transformation? T inverse of x comma y is simply A inverse xy. Right? So you have 1 by 2, 1, 1, 1 minus 1 times of xy. So what is that you are getting? You will get, tell me the answer. You can keep 1 by 2 outside if you want.
X minus xy, x plus y, comma x minus y.
Okay, so this is the T inverse. What is the property it should satisfy? This is the property. Maybe one part I will do, the other part you can try. So here, let's verify this part. So let's do the verification here. What is T composition T inverse of x comma y? What is T inverse of x comma y? We just computed it, right? What is that? It is 1 by 2 x plus y comma x minus y. Right? This 1 by 2 I can bring outside. Now what is T of x plus y comma x minus y? In place of x, I have x
X
plus
plus
y. In place of y, I have x minus y. Now look at this transformation. So you have x plus y plus x minus y, comma, x plus y minus x plus y. Because minus into minus, right? So what will you have? 1 by 2 times of 2x, comma, 2y. Which again 2, if I bring it out, you will have simply x comma y. And what is this? This is the identity transformation, right? I of x comma y equal to x comma y. So what did you get? You got T composition T inverse is equal to identity. Okay. Same way, the homework I am giving is verify T inverse composition T equal to identity. Is this part clear? I just showed that T composition T inverse is identity. Similarly, you do this part. Up to this, is it clear? The composition of linear transformation and inverse of a linear transformation. Are these two concepts clear for everyone? Others?
Yes, ma'am, clear.
Okay, good. Okay. So the last concept is the change of basis. What does it mean? As I already told you, a matrix so far we have seen only with respect to the canonical basis, but we can do it with respect to any basis. Okay. So here let us say u1 and u2 is a basis here. Okay. So u1 and u2 is any basis. u1 comma u2 is any basis of R2. Okay, so you have TU1 is AV1 plus BV2 and TU2 is CV1 plus DV2. So V1 and V2 is also another basis. So V1, V2 is another basis. Both are basis of R2. Okay, and you are writing it like this. So now you are writing TU1. So this is TU1 and this is TU2 in terms of V1 and V2. So this we say it as matrix with respect to this input basis and this is the output basis. So this is the input basis and this is the output basis. Okay. So previously both the input basis and the output basis we considered was canonical basis. Now we can do it with different basis also. So let's try with some example here. So let's say this is a matrix. Write the matrix with canonical basis. So this is the matrix with respect to canonical basis for domain and 1 1 1 minus 1 for codomain. So this matrix already it is like this is TE1 and this is TE2. This is what is already given to you. So what we have
Ma'am,
TE1 equal to, yeah.
how you concluded that this is in canonical basis?
Usually if something is just given as the matrix, we take it as with respect
By
to
default,
canonical.
you take it as a canonical basis.
Yes, when nothing is specified,
Okay,
it is automatically understood that the underlying basis is canonical basis.
okay, okay.
Okay, so now this is what we are having. Okay, this is what we are having. Now let's call this as V1, V2. Okay, what they want us to do is that write T1. Okay, so maybe let's say alpha 1 V1 plus beta 1 V2 and TE2 as alpha 2 V2 plus beta 2 V1 plus V2. Okay, we want to find alpha 1 beta 1 alpha 2 beta 2. Okay, where V1 and V2 are given by this. This is what we want to do. Okay, now how will you write TE1 and TE2 in terms of these bases. This is what is the question. So we already know that TE1 is 1 comma 3. We want to write it as alpha 1 times of 1 comma 1 plus beta 1 times of 1 comma minus 1. What is this? 1 comma 3 equal to alpha 1 plus beta 1 comma alpha 1 minus beta 1. So this gives you alpha 1 plus beta 1 equal to 1 and alpha 1 minus beta 1 equal to 3. Right? If you solve this, what will you get? 2 alpha 1 equal to
2
4.
alpha
So
1 equal
alpha
to
1 is 2. So if alpha 1 is 2, beta 1 is minus 1. Right? 2 minus 1 is 1. 2 minus minus 1 is 3. Okay. So we have found what is alpha 1 and beta 1. Now same way, how do you compute alpha 2 and B2? Same way. TE2 is now 2 comma 4. Now 2 comma 4 is alpha 2 1 1 plus beta 2 1 minus 1. So the equations are alpha 2 plus beta 2 comma alpha 2 minus beta 2. So what is your alpha and beta? Everyone can do this calculation and tell me the answers.
3 and minus 1. Alpha is equals to 3, beta is equals to minus 1.
Okay. So 3 minus 1 is 2. 3 minus minus 1 is 4. Yeah, fine. Okay, please make sure everyone gets this answer. Okay, so now what is the new matrix? Can you tell me? Matrix of T with respect to 1001 for input and output 1 1 minus 1. 1 1 1 minus 1, right? So what is this matrix? 2 minus 1 3 minus 1. So this is TE1 TE2 in terms of V1 and V2. Is this clear? How are we doing this? Is this clear?
Yeah, ma'am.
Okay, fine. All right. Okay, so we are done here. So maybe I'll give you a small homework here to try. A very simple case only I'll give. So let's say you have maybe instead of the transformation, it's a matrix. Let me give the transformation itself. T of x comma y equal to 2x comma x plus 2y. Okay. First find m of t. Find rank and nullity of T. Is T invertible? And then find the matrix of T with input basis E1, E2 and output basis maybe the above basis 1 1 1 minus 1. Okay, try this one to see how far you understood in this session. I tried to cover most of the topics from today's session in one question. Okay, see how far you are able to do this. So let's see whether we have completed all the topics here. What are linear transformation, and how to get a linear transformation from basis vectors, images of basis vectors, and what is the matrix representation of a linear transformation, and then what are range, nullity, rank of a linear transformation. composition of linear transformation, and how matrix multiplication comes when we are representing composition of linear transformations, what is inverse of a linear transformation and how to find it, and then finally change of basis. So all these topics are covered in week 2. So if anyone have any question, please ask now. Yes.
This is not like some. This is just a general question. Like this linear transformation is there, right? Like generally, like how are we going to implement this? Like where are we going to use these linear transformations usually?
Where are we using linear transformations?
Yeah, yeah. Like for what solving what equation we are using this? Like to find some equation of a line or like some sort of something like how usually we are using this.
Okay. So, first of all, as I told you, linear transformation is a more abstract concept. But what was the very first thing we started with? We started with what are matrices?
Okay.
Matrices are the basic building blocks for any data set, right? Any
Mm.
data set, you visualize it as matrices. So, what was the main thing we saw? Why we started with matrices in the first session? Can anyone tell? Because matrices
Okay.
are representing
Yeah, yeah.
linear transformation. So linear transformation and matrices, they are two different representations of the same set, right? The same set, they are different in a set in the sense the same scenario are represented in two different ways. Okay, so linear transformation helps us to see the abstract concepts behind what we are doing with the matrices. Yeah, you take matrix, you have a big data set, you have some matrices to identify the properties of the data set. But how is the matrix doing all these things? What is behind these matrices? They are the linear trans. From this concept of linear transformations, we can understand them. Okay,
Okay.
and this linear transformation, you can see that how they are evolving when we are doing the inner product spaces. You can see how much they are evolving and how much it is helpful in understanding the visualization. In R3 you have a much better visualization. Yes, in R2 also you have, but in R2 you just have lines or origin or the entire R2. In R3 you have a better visualization. You will be able to appreciate the meaning of linear transformation better in R3 maybe. Okay, so linear transformation helps us to see what are we doing with matrices basically, because matrices are the main building blocks for understanding the data sets, right? Okay,
Okay. Okay.
all right. Yeah, any other questions?
It's a general question. Can we get this PDF in which you have all solved all the questions,
Yes,
or the summary
yes, yes. Usually after the session I usually upload it in the notes, which is already the drive
in the
is link.
supplementary section, right?
This is usual. I don't add it in the supplementary session, but in the calendar sheet you have a folder link where I have added all these notes. Okay.
Okay, or in the chat box, right, in the GS space.
Yeah, I have put it in the pin. So in the board, it is there. You can check from the chat also.
Can you share it, ma'am? I am not able to see that. So I joined it late actually.
Can anyone just share the link of the notes folder? Let me open mine. Yeah, here is the link of that folder. Today's note, I will upload it now. Just give me a minute. All the notes in general after the session will be available in this page only. Okay, so I guess now it is there in the folder. Okay, fine.
Yes, ma'am.
Okay. All right. Yeah. So under the linear transformation, the other reason why we are looking at linear transformation is that, see, matrices only till certain extent you can visualize things with matrices, right? So usually in data set we have sparse matrices. What is meant by sparse matrices? Sparse in the sense their size is very huge. You don't have like 2 by 2 or 3 by 3. They are just nothing there, right? It does not really work in real life scenarios. Just for understanding, we can understand with 2 by 2 or 3 by 3. But in the general scenarios, you have like in thousands or in lakhs also you can have. So in those cases, instead of matrices, we can also understand things with transformations. Okay, so that is another reason why we are studying linear transformations. Okay.
This
So
M2 is more based on linear algebra, right? If I'm not wrong.
yes.
Okay, so this. Okay, okay.
All right then. So if anyone else is having questions, we can discuss. Otherwise, we can wind up. Any questions? Okay then. Thank you. See you all.
Thank you,
Tomorrow there
ma'am.
is a TA session. So usually the TA sessions are meant for solving more problems. So try to solve the problems from activity PAGA before the TA session, so that whatever problems you are having difficulty in solving, you can ask in the TA session. Okay, make use of the TA session
Okay,
to
ma'am.
understand problem solvings. Okay, the concepts and all we will try to do it in the instructor session along with some problems, of course, but mainly the TA sessions are for problem solving. Okay. All right then. See you. Bye.
Thank you, ma'am.
Okay, ma'am. Thank you.
Okay, ma'am. Thank you.